So in my opinion, the flight characteristics of this machine are just too good to not be further explored. So I'm actually starting with a investigative full-scale build of this machine. And with investigative, I mean that it could be, halted and cancelled at any time, really, depending on what difficulties I encounter. But nevertheless, I will give it a shot and see what I can do with a DIY approach. So the figure there is not perfectly to scale. It's that would be a 2-meter person. Well, of course, there are people larger than that, but I'm just 172, so I would be significantly smaller in comparison with this figure here. But it gives you a general feeling of the scale of the machine. And my brother kindly asked me where the pilot is supposed to sit, and it's not completely sorted out yet, but I have a good idea of that. And of course, it will be on top here in a seated position in a roll cage. So these tubes will be bent down in the last portion here. So anyway, the only logical way to starting this build, in my opinion, is to start with the most difficult part, because I'm interested in what doesn't work, not what I know I can make work, because I feel very confident about the control system. That's one of the strengths of this machine. It's very redundant and forceful, and I really enjoy the way it handles. It's very connected to the inputs. And so the most difficult part, and the one I'm most scared about is really the gearbox. So I have to build a counter-rotating mechanism, and in this version I only have one motor. And of course, for any kind of endeavor of this kind, you really want to have some sort of fail-safe. It's all about that. You can build flying machines in so many ways, but they will be useless if you have to risk your life every time you use them. They have to be at least one failure safe. So I'm building a gearbox with 4 inputs. So this gearbox is kind of weirdly constructed. I'm driving the big gear, and via the pinion gears I'm driving the lower gear. But in the version that I'm planning on right now, I am planning on having 4 of these inputs here, small pinion spiral bevel gears, and each one of these will connect to one motor that will sit on the sides here. So it's a sort of quad setup. So I will have one motor placed here on each small wing, and a drive shaft going to the small spiral pinion gear here. So the gearbox will have 4 of these small spiral gears driving 2 larger gears, in turn connected to 2 propellers. And just like in this setup, one shaft will go inside the other shaft. So let me show you how far I have come so far with this gearbox build. And just as you might expect, the whole endeavor starts with gathering materials. So here I have my argon and aluminum, and here are the spiral bevel gears. The pinion gear is there, and I have 4 of those, and I welded these 2 short hollow shafts that will connect to the 4 motors eventually. And I turned these axles in my small lathe, and I will show you that later on. I have a pretty limited and small machine park, but it's just sufficient for this build. And it was kind of tricky to find out the right angles from the inside of the gear there, but it turned out pretty good. And I want to weld these without destroying the hardening, so I made a small rotating water bath there that allows me to TIG weld them in a nice manner, and at the same time cooling the teeth of the gear itself. And it turned out okay. It was a little bit tricky, but it worked. So I don't have any live video of me welding those, but the results are encouraging. And here's my new favorite toy, the TIG welding machine. So there's one ready to assemble. Well, I have to turn down a little bit of that weld actually to make the bearing sit flat at the end there, but that's how the weld looks. And here you can see the overall layout with the 4 inputs and 2 larger gear driving the propellers eventually. Here is one of the drive shafts that connects to one of the small pinion gears going to one of the motors. So that flange in the bottom there is going to be connected to the bolt pattern on the one of the motors. I haven't drilled the bolt holes yet. So I start out with just tack welding it in place at 4 points. So I'm like doing the welds on the opposite sides to get as little deformation as possible. Yeah, you have to wait for the post flow of argon there. And after I've done this 4 spot welds, I have to true it up again before I do the final weld. But let's start at looking at the spot welds, the tack welds. So let's take a close look here. Yeah, so these are the 4 tack welds. So they hold the plate there pretty firm, but it's still possible to adjust it with a rubber hammer. So here I'm using my dial gauge to check out for how much off it is, and then I tap it and try to true it up. And I have been using this this gauge extensively through the Gearbox build. It's like a super important tool whenever you chuck something up in the lathe, or you have to like this adjust post welding, or just get to know how much off it is post welding. It's super useful. And right now I'm like hammering on the part, but I've been doing a lot of heating with the TIG machine on shafts to true them up. I think I have the possibility to show you that later on, but it's a very useful technique to heat shafts up to straighten them. And the dial gauge here is just a crucial tool to know what you're doing and see the result of it. So let's jump forward here. So here I've come from being a whole millimeter off to be around, I don't know, it's like 8 or 10 hundredths of a millimeter off. So I'm pleased with that. So now I'm taking the part out and doing the completing the weld on the tacked side. So I have turned down the speed of the turntable, the electric motor there. And let's speed this up a little bit. It's a slow process, but you have wonderful control over the welding process. And it also inspires confidence in the parts that you're assembling, because I have seen with my own eyes both the metal parts melt, and then I added filler rod to that. So I really know that the materials have fused together. It's not any guesswork in that. It's very nice to know that the metal did melt and it did fuse. And here's the result. It's not a big weld, but I think it's strong. And I will just put it in the lathe again and check with the dial gauge, and then I will weld the other side as well. This Megatronic welding machine really makes welding easy. So here it is. It seems to be pretty good. You can see the whole plate there is sort of not on center, but it's oversized, so I will turn it down later on. But it's perpendicular to the shaft, and that's what I'm looking for right now. So then I did go ahead and weld the other side as well. I won't show you that, but it's a significantly long process compared to the model scale. We don't really have to care about stuff like this. Here we're moving on to the main shaft, going to the upper propeller, and it's housing the inner shaft, so I'm making room for bearings inside this shaft so that you have them properly spaced from each other. And here I welded on the larger gear to the main shaft, and here I welded the inner shaft to its bevel gear. And you can see the water boiling off there is just post welding. And anytime you weld, you will have distortion in the material, but it's surprisingly simple to measure the how much off it is, and then you just apply heat and the side that you applied heat on will shrink slightly, so the shaft will bend towards that point of heat, or if you even might apply a little bit of filler, but heat would typically be enough. And with a TIG welder you can just apply heat. You don't have to add any material. It's like a gas torch in that respect. So here you can see I'm significantly off. It's it's like wasn't that like 1 whole millimeter off, I think. So that would be horrible. This shaft will sit in the upper bearing, taking up the thrust forces from the propellers, and if that is 1 millimeter off, you will be shaking like crazy. So I really need to find out in which way it's off, and then apply heat on the other side there to make it shrink in that direction, or bend off in that direction. And it's surprisingly simple, and you'll get a grasp pretty soon. Just move in small increments. It's easy to overcompensate. And this is one of the many wonderful things with taking on a bigger build like this. You're destined to learn a lot of new stuff, and it's so satisfying to get a grasp of new trades, and at least to a hobby level extent master them, so that you can use them in forthcoming builds. Okay, yeah, I mentioned that this lathe is just precisely what the minimum requirement for doing this. So I had to actually, rearrange the machine in the room there to be able to cut away a little bit of the welding for the. It's a tube going from that point up to the bearing, conveying the thrust forces. So it has to sit flat because it will be, perhaps 200 kilos of force or 300 kilos of force applied there. Yeah, and I had to polish up this part of the shaft for the oil seal to work. Yeah, and then came Christmas, and you can sort of figure out what I was doing during the holidays. So yeah, you have to pause for these kind of things as well. Life goes on full broad, and I really appreciate that. So yeah, okay, back to the workshop. I have been using various 3D printed templates to make accurate aligned holes, and that really helps. And here I'm trying to adjust the hole to the perfect size for the pivot, the pinion gear, the 4 pinion gears. Yeah, there's one of them. They're going in from the side there, so I'm just trying to make everything fit as snug as possible before I weld things together. Yeah, so here's the main gearbox housing. Super exciting. And this is the second one, I think. The first one was too much off, so I needed to redo it. And this is, I think, accurate enough for my intentions. Well, I mean, when it comes to gearboxes, you can never have enough precision, of course. This is super low precision compared to what it would be in the mass-produced, industry. But nevertheless, I hope that this will be enough. I put a ring there to make it center in the hole, and drilling away the materials that's left there. Okay, it's fast pace here. We're going forward. And there you can see the thrust bearing in the bottom there. That's the top of the gearbox, so that's where the inner shaft pushes onto. So it's a bearing that's supposed to take axial loads. Yeah, okay. You can see we're getting somewhere. And now the gears are in place, I think. Yeah. Well, at least, what is it, 5 of 6 gears in place. And to make these, yeah, and there was New Year's Eve, of course, yeah. Also important, of course. And it's funny how much longer a project like this takes when you're building. It's just 3 times the scale I built previous, but since it has to be of higher quality and well, it's slightly more complex. It's 4 motors instead of 1, and etc. But it won't be more servos. It's still just 20 servo setup, and so a lot of things haven't changed. But still, the time consumption is like 20-fold or more. Oh yeah, here it's assembled, and yeah, with oil and everything in it. And I'm just test running it to see, well, check for vibrations and sounds and oil leaks. It's actually not leaking any oil. I'm super proud of that. For me, I find that often the simplest things, just as making something oil tight, would be like super challenging for me any normal day. But it seems to have worked to use that kind of oil seal in combination with a polished shaft there. So this machine should be able to take it up to almost its intended RPM, but it's too weak. It's too much friction in the gearbox. So that's just one of many concerns, that the gearbox is too inefficient to be used in a real flying application. But we'll see. There it is anyway, spinning away. And I think I have a measurement here. So I estimate the flight rotational speed to be around 1,480 perhaps, like 1,500 RPM. And after that test, one of the bearings started leaking out a little bit of its grease. I don't know why just one bearing did that. All the other ones look fine. But one was somehow pressured from inside to spit out a little bit of grease. I don't think it's not an airtight compartment as far as I know. I think it's quite leaky actually. Well, not on the bottom side where the oil is, of course, but on other places. So I don't really get how that managed to get squished out. Of course, there are so many steps that I have left out in this short film here. And I really would like to share every part of the process with you and with my future self, but I'm mostly a creative builder. I'm not a cinematographer. I'm not that interested in making films actually. So I apologize for that because I know that I myself really enjoy watching other creative people's processes. So I enjoy that other of you have more patience in doing this kind of recap films and stuff like that. Anywho, I want to share my joy not only with this measuring clock here, that's just so incredibly useful when you're doing precision work. I also have to share with you this set of tools. Yeah, so many of you probably already know what it is, but for me it was like a foreign language. But they are indispensable when you want to measure inside diameters. I really thought that a ordinary vernier caliper was good enough to measure inside diameters in like pipes or bearings and stuff like that. But it turns out this is totally inadequate for that if you want to stay true to the hundreds of millimeters. So you need a set of these measuring tools. So the idea is that you have two spring-loaded parts here, and you can lock them with a screw here. So you put them inside whatever you want to measure, and then you have to lock it first in place like this. And you put it in, and then you open the lock so that these can slide out to the diameter of your part, and then you lock it slightly again, and then you force it to become perpendicular or level with your cylinder, and then you put it out, and then you have your accurate measurement right there. And most people would use a micrometer to measure this, but I found it to work very well with the vernier caliper. So I just place it close enough to my measurement there, and then I let the force of the indirect measuring tool adjust the caliper, and then you get your reading off there. So super important if you want to work with fittings that are like in the hundreds of millimeters, and you perhaps even want to have a heat shrink fitting. You need this kind of measuring device. So and also very affordable, cost effective. It's a great solution for that. So I've been using that extensively as well, dealing with the various inner diameters that I've been working on. Okay, so another interesting thing is a funny thing is that I had a comment here on YouTube. It was someone that enjoyed seeing what I was doing, but sort of was sad about he was into the flight realm by the feeling of the aesthetics of aerodynamics, and I so get it. I mean, I love sailplanes. They are the essence of beautiful design, and this is just it's just not. It's like the lunar lander, but it's not even that cool because you're going to fly it here on Earth. So it's like a Tellus lander, and it's totally horrible from the perspective of aesthetics, aerodynamic aesthetics, and I totally agree with that. But on the other hand, when you fly it remotely, so far, you have the feeling of flight aesthetics. It's really a nice, fluid, aerodynamic feeling in the joystick, in your thumbs. So it has that going for it, but it's a horrible, shaped aircraft. I mean, who doesn't love the Zeppelins or the flying boats or the 40s or a modern sailplane glider? They are so it's just as inspiring your imagination to have like a flying boat for the living and flying in a vehicle, having that vehicle, or the same sailplane that can glide in a slope that a car will not roll down. They are so efficient, and it's a beautiful thing. But this is more. But I have noticed that many people that are into VTOLs, they are going for that aesthetics and that dream of a machine. So it's basically a sailplane cockpit, and somehow it will fly with jet motors or rotors or EDFs or whatever. And I totally appreciate that. I have a background like as an industrial designer, so I can really feel the sense of that kind of nurturing the project with the dream of that super aesthetic, super cool flying machine. But when it comes to real life, when I'm going to pilot it myself, I'm actually totally on the other side of the fence. So I'm completely committed to the flight characteristics, how it feels, how connected it is, and you can do a lot with flight computers, but you cannot, if you have a flawed general design, no flight controller in the world can make that feel agile. You can keep it stable, but it will not be intuitive. It will not be like riding a motorcycle, the way that you feel strong when you're riding a motorcycle. I want that in the flying machine, and also I want the certain form factor and safety factor and a lot of other stuff as well. And so it is what it is. But I totally feel you with my heart that it would have been nice if it would have looked like it feels to fly it. Okay, anyway, I will see you in the next one. Bye.